This is video 1 for the Drivetrain design unit. So for the learning goals for this unit, I want you to be able to calculate static and kinetic friction. I want you to be able to discuss the different types of steering systems and explain turning torque and turning scrub. So to begin with, we need to talk about friction. This is one of the most important parts to designing a drivetrain. What friction is it's a force that opposes motion when two surfaces slide past each other. It is a reaction force only. So if an object has no force trying to move it, there will be no friction, which is kind of handy if you think about it. And it only occurs when the two surfaces are in contact. Now we have two types of friction, static and kinetic. There's also rolling friction, but that's so small it's negligible. So we got static and kinetic. Static, which means stationary, is basically when an object does not move, and kinetic, meaning motion, is for objects that are sliding. So looking at this graph here, on the x-axis we have the applied force, and on the y-axis we have friction. So to get an idea, so let's say I have an object right here. The applied force would be an example of, like, say someone tied a rope to this box and they started pulling on the box. The friction would be the force between that box and the surface. So what happens is you start to pull on the box, and as you start pulling on the box, because friction is a reacting force, the static friction pulls back against. And the harder you pull on this box, the greater the friction is between the box and between the floor. Now there is a breaking point right up here. This point up here is the maximum static friction possible. Once you reach that point, the box will break free, and then we get some kinetic friction. Notice that the kinetic friction is less than the maximum static friction. So once you break an object free and get it sliding, it's easier to keep it moving. Now, what friction really does is it converts mechanical energy into thermal energy. So there's going to be heat generated between the two surfaces as they slide past each other. You've probably noticed this when you rub your hands together. Now, the way we calculate friction, it doesn't matter if it's static or kinetic. Friction equals the coefficient of friction, that's a number you'd look up, it's unitless, times the normal force acting on the object. Normal forces can be a little tricky. Basically, a normal force is a surface pushing up against an object. So going back to our box up here, the normal force would be the ground pushing up on the box. So, and also this formula, again, it works for both. So if I have the maximum static friction, it equals the coefficient of static friction times normal force. And likewise for kinetic. So every surface has two numbers, a coefficient of static friction and a coefficient of kinetic friction. And we can think of this as how much grip, this mu, and that's what it is, the Greek letter mu. We can think of it how much grip the surfaces have. The stickier the surfaces, the greater the grip, the higher the value of mu, which is the symbol right here. The smoother the surfaces, the lower the value of mu. So looking at a couple diagrams then, for a box that's on a nice horizontal surface, the normal force will equal the gravitational force, or how much the object weighs. So the normal force would be mass times g. If I have a box on a surface, or on some sort of inclined plane, notice that the normal force is not how much the object weighs anymore. This is where we get to do a little bit of math. We have this component, I'll call it FGY. It would equal the cosine component. So the normal force would equal this y component. We won't do a whole lot with this, but it is something worth mentioning. So let's say we want to conduct a quick little experiment to find out what is the coefficient of friction between, let's say, the high traction wheels and the floor. Well, what you would do is you would take your robot and set it up on a ramp. And you'd situate it, sideways so that it doesn't roll down the ramp. And then you would increase this ramp. You would lift it up until it begins to slide. And what you would find is that tangent of that angle where it begins to slide would equal the maximum static friction, or the coefficient of static friction between the wheels and the surface. Now you would have to make sure that you use those mats that we use at competition on the surface of the ramp, but it's a pretty simple idea. You just kind of lift up the ramp until it begins to slide, record that angle, tangent of that angle will give you the coefficient of friction between the robot wheels and the mats. So we can use this to start talking about something called traction. Traction is the amount of friction between the drive wheels and the surface it's rolling on. You can also think of it as the amount of force the wheel can exert to the surface before it begins to slip. So here is our wheel. And on our wheel, we have a motor or a gear system or whatever, and it's applying some torque. So since it's applying some torque, there's going to be a force being applied to the ground. This wheel has a radius. So looking at this, torque equals a force which is perpendicular to a lever arm. I'll make this a capital R for radius. So looking at this, we see that our lever arm distance is going to be the radius of the wheel, and the force is going to be the force applied to the ground. So this torque equals this applied force times the radius of the wheel. Now, this wheel, if you look at the very, very bottom of the wheel, it's kind of pushing to the right. So friction, which opposes motion, is going to the left. Now keep in mind, the robot is going to be moving in this direction. So this is something that's really kind of counterintuitive. Friction points in the direction of motion. And it's because for this drive wheel, friction opposes motion. So this friction is pointing forward, which, again, it even boggles my mind to think about it. Now, also at the bottom of the wheel here, the robot has some weight, which means that there's a normal force acting on it as well, where this weight equals the mass of the robot times 10, G is 10. So looking here, we see that the normal force is going to be the same thing as the weight, which is mg. Now I say that because this friction equals the coefficient times the normal force. Now this friction, this is actually going to be the maximum static friction. And you may be thinking, well, wait a second, the robot's moving. How could it be static friction? And yes, the robot is moving. However, the wheel is not slipping. This is the key to understanding traction. We have to use static friction. We do not want the wheel to slip relative to the floor. So that means that since it's stationary, we have to use the static friction. Now, we have two forces at the bottom of the wheel that are kind of important. This static friction and this force being applied. Now, if this force that we're applying to this wheel is greater than the maximum static friction, we get slippage. So in other words, the wheel will do a burnout, if you want to say. If this friction is less than, or this force is less than the maximum static friction, then the wheel moves. And there's no problem. But what we're interested in is the maximum force we can apply to the ground while this robot, while this robot can move. So what's the maximum force we can apply? So that means that we want this force, this applied force, to be equal to the maximum static friction. So this is what's important right here. We want to make sure that this force is equal to the maximum static friction. So then coming back up here, our torque, which equals the applied force times the radius of the wheel, we're going to modify this and we're going to say, okay, now we're interested, that force needs to be equal to the maximum static friction. But the maximum static friction is the coefficient times the normal force. So we have torque equals mu times normal force times the radius of the wheel. But remember that the normal force is equal to mg, so we're left with the torque equals mg, sorry about that, mu times mg, times r. So basically what this formula calculates for us is it calculates the maximum torque we can apply to the wheel before the wheel loses traction. So looking at that formula, what are some ways we can increase the traction? So in other words, how could we apply more torque to the wheel before it starts to lose traction? Well, we could increase the coefficient so we could get stickier wheels. That would do it. Probably misspelled that. I think it's IE. We could have a larger robot. So if the robot had a larger mass, okay, we can move to a bigger planet. Obviously we can't change G, but if we were to go to Jupiter or some planet that has a greater value of G, we could have more traction. And really, you know what? We can go to a different planet. If we're sending a robot to Mars, G is less on Mars. So that is something we could change, to be honest. And then finally, we can move to bigger wheels. So those are some ways that we can increase the traction of our robot. That will conclude video 1.